Okay, make sure you guys sign in. And I'm going to go ahead and start this way. Yeah?
We don't have a sign-in sheet. No one makes one, we do.
Yeah, somebody just pass one around. And is Ken there?
Yeah, we've got one started.
Okay, cool. Not a problem. Thank you, I appreciate it. Okay, I'm going to go ahead and do the desktop computer here. Okay, so this is your Blackboard. Okay. Just to let you guys know, my son actually teaches psychology. He's actually teaching brain developmental psychology at Oklahoma State this semester. He's actually working on looking at the changes in brain chemistry due to learning. He decapitates bees' heads for a living. Go ahead and just leave it towards the back to make sure everybody gets a chance to sign in. So he actually decapitates bees' heads so that they actually look for the brain chemicals associated with learning. So learning does change your brain.
You're breaking up kind of bad here in talk wall.
We'll try again.
Sometimes if you mute your student mic, sometimes it comes in clearer.
Okay, try this. Is this one better? Okay. This light was kind of flickery, and now I've made sure it's staying on. So it's staying on. So my son studies brain psychology, and he's doing experimental psychology and is looking at brain chemistry. So learning is not easy, and because physics is a different language, okay? You all thought chemistry was a different language. Physics is a real different language. The language of physics is mathematics. Fundamentally, it is mathematics. There's a case, depending on which physicist you're looking at, depends on whether he developed the mathematics to explain the physics, or the mathematics was developed and the physics came later. So mathematics truly is the language of physics. And so we've done people a disservice from a conceptual point of view as we've taught physics last in high school. We start out with earth science, and then, if we're lucky, but most of the time we start out with biology. I am not a biologist. I hate biology. There are too many variables. Okay? That's why you can't put mathematics to biology. There's too many variables. The old joke is a physicist describes a cow as a sphere with the milk evenly distributed throughout, because there are too many variables. But we teach biology first because we don't have to have the mathematics. Our mathematics skills have been broken from our science skills. And so we teach biology first because it tends to be observational. We teach chemistry next because the math is mostly just college algebra a little bit, word problems. It's word problems and conversions. Then we get to physics, where the math and the problems are linked together greatly. So it's an interesting. We've done a disservice to most everybody when we've done it and doing the teaching. But physics is fun, and we keep working on it. So let's look at Blackboard here. There were some emails that went out, so we're going to kind of hit on a couple of high points. One is the NASA Community College Scholars Program is now open for application. Both NOC campuses have had NASA scholars. We've had people that have actually gone to the 2-week program at NASA. We've had people that have gone to just the 1-week program. We've had a variety of folks go, both from the biology side as well as the physical science side. So these are open now. The application is there, and I posted the link to the page in the announcements. The other thing is, I don't know if you all are aware that NOC runs global education. Most of it's run off of the Stillwater campus, but anybody can go. It's also members of the community can go, because we are a 2-year community college. So any members of the community go. All you have to do is sign up. There are courses for credit that can be taken as options. those of you who may up at Oklahoma State who need the I credit or the I designation, all of these courses have an available credit hour course that can qualify for that I. I happen to be leading the one that's going to Berlin in the spring of 2020 over spring break. It will be focused on architecture. We actually will be meeting with 2 architecture firms. So that's something that some people are interested in. But we also have a variety of other ones. There's the Great Wall of China, there's Cuba, there's Dublin, there is the Natural Science Lab. We have an instructor out of Stillwater that goes to Belize every year and does that class. So there's a variety of different classes that are in there. They are reasonably priced. I know it doesn't look that way when you first see that chunk of money right at the beginning, but if you ever go price an international airfare ticket and look at 7 days in a hotel in a city like Berlin, the price of the tour is less than that. Plus you get some meals, plus you get your tour guide, and you get your airfare. So, I mean, it is reasonable. NOC does require one of the additional expenses that you don't see on the study abroad pages. NOC does require you pay for the insurance, but that is a reasonable insurance cost, and we have seen it save people over and over and over again. So it's just something that's really prudent to do. The reason I'm bringing it up is it's a $95 registration fee. That's the only part that's non-refundable. If you can't come up with the rest of it, is that registration fee. I do know that the Berlin trip as of September 1st will increase by $25. You can lock in your price and by just putting in your registration fee, set up a payment plan. Through the college study tour group that we have, there is a GoFundMe page that you can send to family, friends, aunts, uncles, those things that say, I'm trying to raise money to go on this trip. And my understanding from Mr. Watkins, who's run these over and over again, that those work out really, really well. So if you're interested, that information is out there. So that's on our global education page. If you weren't aware, there's our Dean of Global Education. And so we have a lot of opportunities. And if you've never been outside the country, I encourage you to do so, because you learn a lot just by going. You really do. Okay, so now let's go back here. So under week 1, you have, oops, I'm in the wrong class. This is the chemistry class. Let me go. Under week 1, if you're having trouble accessing WebAssign, please do not forget that you can access WebAssign directly from Blackboard. And you can get in there. And I will tell you that we have 57 people total in class. I have 57 people in Blackboard, but I know that I have a number of duplicates where people have registered twice, and that happens because of how you get in and how you register, that happens. So if I have duplicates and the numbers are the same, that tells me, even though I haven't gone down name by name, that there are a few of you who have not accessed the homework. That's going to be a problem for 2 reasons. One, if you don't access the homework, it's going to make it hard for you to do something on the test, because I am notorious for giving problems that you have seen before on the test. So if you haven't even gone into WebAssign to see the problems, you're going to come into the test cold and you're going to go, oops. So that's problem number 1. Problem number 2 is homework's worth 20% of the grade. Quizzes are worth 20% of the grade. Laboratory is worth 20% of the grade. 60% of the grade is something that you have total control over. Total control. Remember, my grading scale is shifted. So if you can get a good grade in lab, get a good grade in the homework, and get the extra credit on the homework, which really helps out in the long run, get good grades on the quiz, the odds of you getting a C or better in this class are much, much improved. I have never seen anybody who hasn't done any homework actually pass the class, even with a B. So, I will be going over the weekend to see if I can figure out who it is that's missing. Because I will be sending out early alerts on that. Because if you're not doing the homework, you know, you're not going to get anything and you're not going to get anywhere. Because physics is all about practice, practice, practice. So there's that aspect of it. So there's the web sign part. So if I go under here, under course materials, and you go into week 2, I have added a folder that says based on the questions that I got in my email. Based on the questions I got in my email, I've given you some additional resources. Both of these are from the organictutor.com or YouTube channel. He is very, very good, has lots of extra information. If you click on the crash course in trigonometry, it will take you directly to his one course with the ads, right? So you get there. So he actually has the material. One of the other things you might want to do is click the subtitles. And he will work through it, and you can actually look at those pieces. I also went and looked at where people were having trouble on the homework. So that's one thing that's there. One of the places that people were having trouble on the homework we'll actually look at some problems with today. But here is in the general chemistry introduction, which is one of the reasons that I didn't spend a whole lot of time on it in lecture, is because we spend, at least I do in my general chemistry class, the first 2 lectures are spent on precision of numbers, working with significant figures, and actually doing calculations with significant figures. So I do it in my chemistry class, not necessarily my physics class. But over here, if you look at this, there's one on scientific notation. Here's one on significant figures made easy. Here's one on conversions of units. So if unit conversions happen to be one of your challenges, that's another one that's out there. Here's one on the metric system review. And you can see some of these range from, fairly lengthy to some of them only are 10 minutes to some of them are 5 minutes depending on what the specific topic is. But he has the organictutor.com, or this organic tutor guy, has a bunch of individual YouTubes that may help you. Okay? So that's just some extra resources, and I try to do that in order to get things that are there. So if you go to WebAssign, your student view looks like this. The pre-work for Chapter 2, the whole purpose of pre-work is to get you to see the material before we start covering it in class, so that you're getting familiar with the terms, you're getting familiar with the concepts that we're working with, getting familiar with those kinds of things. And if you didn't catch it, homework was pushed until September 3rd. I haven't gone in to push the button to have it regrade if you were working on homework yesterday, so you didn't get the extra credit, but now you will. I just have to go in and push the button to have it rescore. But again, I caution you, if it's, for some of you it was a technical issue getting into WebAssign. We could have worked that out ahead of time. For others of you, it was, just think about opening it up. I do encourage you to print it out. Take the piece of paper, print it out, particularly those of you who have sports, those of you who have other obligations like band, have other travel, those kinds of things. That way you have the paper copy that you can always work on. And if, like what's happening over the weekend, the internet happens to go down because we're having storms, you have an opportunity to be working on your homework on the paper. Okay? So that does help. So any questions about extra things that I've added, or you guys over there in Tonkawa good? All right. And I will be in my office right all day Tonkawa on Tuesdays. So, and please guys, please help me. Tell me which side you're on. I mean, you guys were really good about telling me you were in Physics 1. That helped a huge amount. That at least got me into the right box. But when I was answering a question about, hey, I'm in my office right now, doesn't, you know, it's a little tougher if I don't know which side you're on. All right, let's see if I can go to the document camera. That seems to be the challenging one. Okay, I did get questions about problem number 12. First of all, you're lucky I remember what problem number 12 is. Partially because I got so many questions, I went and looked up problem number 12. It does help me if you give me a couple of word warning of, this is the gal walking through the mountain. Alright? Please go to the end of last Friday's lecture, because I set it up. Okay? And now after you've struggled with the problem, going to the last Friday's lecture to actually see a bit and pieces of it, might make a little bit more sense. Also, I think in my YouTube playlist, you might go back. I think I may actually have a cutout snippet associated with that problem. So there's a couple places that you can go to get a little bit extra help there. But I'm going to actually work a problem because another problem that people had was just some of the basics. So what I'm going to do is we have a wall. Okay? So we got a wall here. And we got the ground, and we're going to assume the ground is horizontal, so that means that I have a nice right triangle. Okay? So this is my good old wall. I'm going to lay a ladder on here, and it's partially extended. So we're going to represent our ladder with a as the hypotenuse of the triangle. I don't have, all I got on my person for my MacGyver type toolkit is I happen to have a protractor. Well, I could measure the ladder with the protractor, but I also have a couple other things that I have at my disposal. One is this wall has some marks on it, and I happen to know now that at the top of where I've placed my ladder, that this distance is 8. No, we're going to make it 2.8 meters. I just happen to know that because of things that are on the wall. And my protractor tells me that I can measure this angle, and it is 25 degrees. I want to know the length of the ladder, and I want to know how far away the bottom of the ladder is from the wall. I have all the information that I need to figure that out. As long as I have two sides of a right triangle, two angles of the right triangle, if I have two pieces of information about this triangle, I'm going to be able to figure out the other information, provided it's a right triangle. Okay? Right now we're sticking with a right triangle. There is another trigonometric proof that we can use, and that's called the law of cosines and the law of sines, and I don't necessarily have to have a right triangle at all, but most of the time in General Physics 1 we're going to be working with a right triangle. But when I'm dealing with triangles, I can do a lot of things. So, if I want to know the length of the ladder, we have our handy dandy toolkit, because you've started writing out your cheat sheet that you're going to be using to help yourself work the problem, so you don't have to be flipping back and forth in your book. You don't have to be flipping back and forth in your notes. Those of you, because a lot of you are biology types, biology types seem to be using the 3x5 cards a lot more than anybody else, because you got to memorize parts of the body, and so you're using them as memory aids. You might want to take a 3x5 card and make one, but you're already used to doing that. So I've got my handy dandy toolkit here. So if I look at what I have here, this is the opposite side because it's opposite the angle. This is the adjacent side because it's sitting there adjacent to the angle, and this is the hypotenuse. So now that I know that, I can go over here to my tools and I go, oop, the sine is the opposite over the hypotenuse. Alright? Sine of the angle is going to be the opposite over the hypotenuse. This is known, that's known, this is my unknown. So I got to rearrange my equation to get things right. And I did skip a step. So I just rearranged my equation. So now I can plug in numbers. So this is 2.8. Sine of the angle is 25 degrees. Now I get my handy dandy calculator out. Now, this is important because you may or may not know that your calculator has multiple functions. If you look at my calculator right now, I'm going to scroll in. See if I can get the glare. You will see that in the bottom it says RAD. If I do this calculation with that designation and I plug it into WebAssign, WebAssign's going to go, you missed it. And you're going to go, how could I possibly miss it? I'm doing it just exactly the way she showed me on the screen. The reason is because my units here are degrees. My calculator is set in radians. Radians and degrees are not the same unit system. So I have to go over here and push my little button and make sure I'm in degrees and make sure my calculator is actually in degrees. And for those of you who remember, if I take a circle, this is 0 radians, this is pi radians, a complete circle is 2 pi radians. It's just a different way of representing degrees on a circle. We're used to 0 to 360, but there are times, and when we get later on in the semester, we're going to be using radians because it makes more physical sense than using degrees. We can convert back and forth all we want to, but we will. So the first thing you want to do is you want to make sure your calculator is in the right unit system. So now we're in degrees, and this works out really well. And I'm going to take my 2.8, I'm going to divide it by, and depending on your calculator, this is the next thing you got to worry about. I may have to put it in parentheses, I may not have to put it in parentheses, I have to make sure that it's calculating correctly. So I'm going to put in the sign of 25, hit the enter button, and it says that that's now going to be 6.63 meters. Now this is physics class, so while I am not as terribly concerned about significant figures, let's start talking about significant figures. Significant figures, if you remember from chemistry class, tells you the precision with which the number was measured. Because if I have a penny, the standard weight of a US penny, as it leaves the mint, is 2.55 grams. Now if I'm in physics lab, most of the physics labs weigh to plus or minus 1 gram. So if I put a 2.5 penny on a scale that only reads to 1 gram, my scale will read either 2 or 3. That's a whole gram that has the potential to have error in the number. So the precision of the number is where my mark is going to be that tells me how much potential error. So this number, the error would be in the 8. This number, the error is in the 1 gram part. So significant figures relates back to the precision of the number. And in this case, I've got two significant figures. So if I'm doing my calculation, if I'm adding, subtract, or if I'm multiplying or dividing, I go with the lowest number of significant figures. This number should actually be written as 6.6 meters. Okay, so I'm going to do something else real quick, just because I want to do it. All right. So, let's take another number there. So we can calculate that. Let's also figure out how far away. I can then do the tangent of the angle is equal to the opposite over the adjacent. Rearranging, I get adjacent is equal to the opposite divided by the tangent. And now I get my 2.8 divided by the tangent of 25 degrees. If I put that in my calculator, and that's going to give me 6 meters.
Can you zoom out so we can see?
Just a second.
Okay.
That's going to give me 6 meters. And I think it was problem 9 that was actually doing the exact same thing. And it was a tutorial problem. So if I give you a tutorial problem in WebAssign, it's actually designed to take you step by step by step. So hopefully that helps clear up a little bit. You guys good? Any questions? Okay, so now let's take another one. So what I'm going to do here, I'm going to write pi. That's 3.141592654. At least that's what's shown on my calculator. You know, I could probably go pick up a handbook of mathematics and get it to a lot more digits. I can get it to multiple digits. But if I'm asked to write this in 3 significant figures, 8 significant figures, or 5 significant figures, this is going to be 3.14. This one will be 1, 2, 3, 4, 5, 6, 7, 8. This will be 3.1415. Where's 5, 9, 2, 6, 7, 8. And this one will be 3.1415, except, oops, I got a round. And that's going to end up being 3.1416. Because I have to round. What?
You drown on the 8.
Oh, yes. So there's round 7. Actually, depending on the convention, I might round down to it might stay just 6. Okay? Because the conventions that we use, that's why I said it might stay just 6. Because it's 54, we probably rounded to 7, at least that I have written. But it might stay 6 because if I didn't know this one, I was just at the 5. I try to round so that the last number is even. Okay? I try to round so the last number is even. So half the time I round up, half the time I round down. So this one may be dependent on the convention. So remember, significant figures, if I do 0.00368, this only has 3 significant figures. Because that 0 and that 0 are placeholders. Because I could rewrite this as 3.68 times 10 to the minus 1, 2, 3. And every every number in front of my scientific notation is significant. Okay? Now, I will warn you that when you were probably trying to do the homework problem, you might have gotten a formatting error in WebAssign, because WebAssign, if I'm writing this, and I've got a number like this, 6.89348, and I'm going to write it down as 6.89 times 10, and this would say times 10 to whatever. It's going to be this times 10 to that spot, or you'll have it as e to that whatever number, and it could be a formatting error. If you think it's a formatting error, take a picture, send it to me, and I'll double check and look, because I do know WebAssign sometimes can be very, very persnickety. But you can always go back to that getting started with WebAssign to look at the format to get the number in. Okay, when I'm adding and subtracting, so I have like 527, I have 6.1, I have 0.911, and I have 4,036 I'm going to go ahead. Now, this is one way to distinguish that I actually have written this to 4 significant figures. This is not just a placeholder. That one's not just a placeholder. Had I not put that decimal point there, you wouldn't know that that's just a placeholder, and that this would be the digit that would be the least significant. By doing this, I've actually told you that that's a significant figure. So if I go ahead and plug this into the calculator, I'm going to get 1, 1, 0. I'm going to carry my lovely 1. This becomes 4. I'm going to carry that. That becomes a 7. I get that carried. That becomes 9. That's the number that my calculator would give me. What I'm going to report is 4974, because when I add or subtract, I keep the position of the least significant number. Okay, so I'm going to end up losing this stuff over here, because these two, my position of the least significant number is there. So when I add or subtract, that's what's going to happen. When I multiply and divide, you go with the least significant digit. So I can do 2.8 times 36.95. If I do that, which is going to give me a number like 2.8 times 36.95, this is going to equal, on my calculator, 10346. But this is only 2 significant figures, so I'm going to actually write this as 100. But I can't tell you which one it is, so I'm probably going to have to write this as 1.0 times 10 to the 2 to be able to communicate that that 0 is significant. Now, we aren't going to have to concentrate that much on significant figures in here, but there are certain times that we are going to be doing some things to show the differences between numbers, and we will carry it out to 4 or 5 numbers past the decimal place so that you can actually see the differences. But most of the time your answers are going to be in 3 significant figures, because we're not worried so much about whether or not the penny is 2.500 or it's 2.5 for the purposes of what we're doing. And it's related back to the purposes for what we're doing. Okay? So does that help those of you that were struggling with significant figures? And I encourage you to, if you're still struggling, Appendix A of your book has the rules for significant figures and has some examples. And the tutor.com portion does too. Or that. And you do, speaking of tutor.com, you guys do have access to tutor.com. If you've read it and you know how to access it, it's from the, over in Blackboard, you can access tutor.com. They're there all the time so that you can access them. And a lot of times, even though the math people don't say they are, a lot of times what's your problem with the physics problem is it's a word problem, and a math tutor may be able to help because it's basically just pulling out that information from a word problem, not necessarily a concept issue. So we're going to do that real quick. I'm going to start with this. This is the problem we're fixing to do, because I'm always fixing to do something. We've got a surveyor that wants to measure the distance across the river. We're going to use a tree on the opposite side as a reference. We're going to make the assumption that the river at this point is reasonably straight. And we're going to walk for 150 meters, and then we're going to sight back to that tree as a reference point. And we want to know how wide the river is. Okay? You know, usually what they always do, the joke is, what did he have for lunch, right? I don't know. That's not giving me the information. But I have all the information that I need to work this problem. I do. So the first thing when you get a physics problem is you read the problem. So let's read it again. You got a surveyor. He wants to find the distance across the river using the tree as a point of reference. So we've started to draw that mental picture of what's going on. So let's think about it. So we're going to draw our picture. So I'm going to draw my picture. So here's a bank. Here's a bank. I got my little guy or my surveyor sitting over here. Okay. I am not an artiste. We just say that right now. And over here I have my tree that's relatively near the bank, right? So there's my tree. So now I've got an idea of where I'm starting from. He's going to use this tree as a reference. And then we're going to walk. And this is going to be 150 meters.
Is the answer 93.7 meters?
I don't know. I haven't calculated it yet. I don't know. Okay. Judging from my little number, it probably is. But I'm going to walk 150 meters. So we go back here, and then we sight back from this spot. That we've got, and they said that was 35 degrees. So now I've got
35. This is 32.
32. All right, you're right. It's Friday. I've had a long week.
Understand.
I didn't get home until after midnight on Wednesday. I didn't leave campus until almost 10 o'clock last night. And then I had to get here by 7:30 this morning. So it's 32 degrees. So I've got myself a right triangle. So basically the problem, so you read the problem, we draw the picture, we label the picture. Then we have to figure out what it is we want to know and what it is we don't know. We want to know this distance right there. That's the distance we want to know. And if I go ahead, for those of you, this is the hypotenuse, this is the adjacent, and this is the opposite. So now I got to figure out which equation that I have in my toolkit that's going to allow me to help. Well, if I've got the adjacent and an angle, I'm probably going to want to use cosine, because cosine of the angle is my adjacent over the hypotenuse. Oops, that's not quite right. I want to use tangent because I don't care about the hypotenuse. I could do it in 2 steps, but I'm going to go ahead and use tangent. And tangent is going to equal the opposite over the adjacent. I got it. Now, your book is going to tell you at this point, rearrange the equation in terms of its symbols, and then plug in the number. In this case, that's okay. We will get to problems down the road that it may be beneficial to go ahead and put numbers in early and then rearrange it, just because you're not keeping all those symbols all the way down and having a tendency to lose them. So at this point, you get to make a judgment call. But for us, we're going to put our adjacent times the tangent and get our opposite. Now I'm going to go ahead and plug in the number. So I get my adjacent is 150, my tangent is 32. Plug that into my calculator. I get my 150 times my tangent of 32 degrees. And as you said, it was 93.7, and that's in meters. Kind of gets me starting. Clean up all my scrap paper. Now, the other part of the homework for chapter 1 was estimates, and we played with estimates. So hopefully, but that didn't seem to be the biggest issue that I was seeing so far. So I'm just going to progress on, and we're going to start the next chapter. Okay? You good? All right. I'm going to change pins because pins do a little weird things. Also, okay, so we're starting with motion. And what we're going to do with motion in this case is we don't care, at least right now, of what's causing the motion. We're not going to care what's causing the motion. We just know that we have motion. And we've done this a long time, because if I tell you that you're going to travel 50 miles at a speed of 3 miles per hour, and you travel for 3 hours, how far did you go? Well, actually I said 50 miles, didn't I? I actually gave you all the information. But if I'm traveling 3 miles per hour for 3 hours, how far did you go? Come on. You traveled 3 miles per hour for 3 hours, how far did you go?
9 miles.
9 miles. Okay? It wasn't a trick question. Wasn't a trick question. So the first thing is, don't make it harder than it is. Okay, step 1. Don't make it harder than it is. So let's think about it. If I have a pound of feathers and I have a pound of lead, which one weighs more? They're equal. Okay? Now which one has a bigger volume?
I don't know. How are you storing the feathers? I mean, that's a big
Well,
question.
I like that one. That's how you're storing the feathers, you know. So, but most likely the feathers is going to be a bigger pile than the lead, right? You know, because but I could store my feathers. I could compress them. But the first thing is, you do more physics in your head every day than we'll ever be able to write down. I got soccer players, right? I got soccer players. I don't have any soccer players. I have baseball players, right? I know I got baseball players, and I know I got basketball players. I got soccer players. When you go up to kick the soccer ball, and you're lining up to kick the soccer ball, you are figuring out the trajectory of that ball, so you're already figuring out the angle. You're figuring out how much force you have to apply to the ball in order to get it the distance down the field that you want it to. And you're probably doing that at the same time you have a defender running at you. Think about all the physics you have just done. You've done a great deal of physics. Now, if you're an equestrian, a person who rides horses, here comes the really fun part. Not only are you doing the physics for you, you're doing the physics for the horse. So if I'm coming up to a jump, which my daughter would do, my daughter actually does jumping, she comes up to a jump, knows where she's got to position that horse, knows what angle she has to bring the horse in, the place where she's going to jump the horse over the fence to get it and position the horse to take the next jump. She's doing all of that in her head before she can even be able to put it on a piece of paper. So you do a lot of physics in your head. So first thing you want to do is when you do a problem, is it reasonable? And I will tell you, and I will be the first one to admit, when I do a problem and I'm making up numbers right here on the spot, they may not turn out to be reasonable because my numbers weren't reasonable to start with. I didn't give you a reasonable mass for the car, or I didn't give you a reasonable height for the building, or I didn't give you something that was reasonable. But most of us can take that and say, is this reasonable? So when we deal with motion, we have to look at what's reasonable. So the first thing that we want to deal with motion is we want to know where we start and where we finish. Right? If I'm moving something, I got to know where I start and I got to know where I finish. Now that's the trick. Okay? That's the trick. Because this is where we're going to start to deviate from things that you normally think about. One is we're going to use a term called displacement. Displacement is not distance traveled. Okay? And this is where we tend to get confused because a lot of times displacement is distance traveled. But most of the time it's not. Okay? Displacement worries about where I start and where I finish. And that's all it cares about. Everybody remember Hess's law. Back in chemistry, and we're doing our thermodynamics in chemistry. There's this weird thing called Hess's law, and that weird thing called Hess's law, we didn't care how we got up the mountain. We only worried about the fact that we went from the bottom of the mountain to the top of the mountain. Didn't matter what number of steps we took. Didn't matter whether we took the straight path or the curvy path. We only cared about where we started and where we finished. Same thing here. Displacement only cares about where we start, where we finish. So you'll encounter a problem that looks like this. I got a swimming pool. Okay? And the swimmer is going to go up and back. And we're going to calculate two values for that. We're going to calculate something called velocity. And we're going to calculate something called speed. Now the displacement of this swimmer is 0. Because the swimmer has gone right back to where he started. The distance traveled, if this is a 50-meter pool, the distance traveled would be 100 meters. Okay? And if it took this swimmer, we'll give him a slow, like it's doing the breaststroke. We'll do, and again, this is when I'm making up numbers, right? We're going to say it took 35 seconds to do this 100 meters. I don't even know if that's reasonable or not. The velocity is going to be 0. The speed would be that 50 meters times 2, because he did 2 laps of the pool, you know, an out and back, divided by 35 seconds. If I do that, that's 100 divided by 35, and I can't do that one in my head. It's going to be 2.86 meters per second. Now, we've done speed problems all the time. For example, if I'm going from here to Norman to go to the OU game, and I know I'm going to average 45 miles per hour, partially once I get to Oklahoma City and the traffic's going to back up, and when I get towards closer to the stadium in Norman, we know the traffic's going to back up. And so I know I'm going to probably go to an average of 45 miles per hour. I want to know how soon or what time I need to leave from here in order to make it to the game on time. So I got to know the distance that I'm traveling by my route, as well as that average speed in order to get there. And we do those calculations all the time. I mean, you do those calculations. So velocity is going to be 0, but my speed is going to be different. So let's talk about displacement. So displacement is going to be, and we're going to use, since we're in one dimension, it's not going to matter whether we're going horizontal or vertical. We're going to go ahead and use x to represent that displacement. This delta means change. So my change in position is going to be my final position minus my initial position. And we tend to use subscripts so that we can keep track of what my things are. So and this is displacement. Now, displacement can be a vector. So a vector, we usually represent a vector like that, using an arrow. It has a head and a tail. Vectors are unique things. Vectors have magnitude and direction. And I think we talked about going back and forth between Cartesian coordinates and polar coordinates. I think we talked about that already, because we talked about why we want to look at this. But my vector's got magnitude and direction. When I'm traveling only in one direction, we know it's either going forwards or backwards, right? Or I'm going up or down. But I can do some cool things. I don't have to be in a lovely Cartesian coordinate system. I can be on an inclined plane, and I'm actually only traveling back and forth along the top of that inclined plane. So I'm still only traveling in one direction. I just have got to orient myself so that I've got my conditions just right. So we're looking at motion in one dimension. It can be forward and backward, it can be up and down, it can be along an inclined plane. We can look at a variety of things. So my displacement is where I start and where I stop. Total distance traveled, another beast. Because I can go this way and back, and this way and back, and this way and back. And my total distance traveled would only be, because this is where I started, and this is where I finished, over here. This would be my displacement, but my total distance traveled is however I weave back and forth. Now, when we look at speed, speed is a different thing. It's a different beast. Speed is actually defined as total distance divided by time. Speed is not a vector. There's no direction associated with it. And this is where we get confused, because we use speed and velocity interchangeably. We use those terms interchangeably in our real life, but in physics they have distinct meanings. So velocity, we're going to use the letter V. It's a vector. We generally represent it with a little line over the top. Velocity is defined as the change in position, or my displacement, divided by the change in time. So if I'm writing this out, I get x final minus x initial divided by time final minus time initial. And everybody's had their first lab, right? Everybody's done the first lab, and you did a motion lab, right? And in that motion lab, you ended up looking at a couple of graphs. And this was time. And this one was position. And then one of the graphs you looked at was velocity. And position is in meters, this is in seconds, this is in meters per second, and this is in seconds. Now, if I have something that looks like this for the first second, and it's going flat, what is physically happening here?
Nothing.
Nothing. They're just standing there. But then, if I end up with something that looks like this, I'm moving, right? And because it's a straight line, we call that a constant velocity, right? Because it's moving in a straight line, it's constant velocity. I can figure out what that constant velocity is by doing my rise over run. And this is a change in x over a change in time. Graphically, it's the same thing here. And so in this case, I have a constant velocity. And if I look at that on this graph, I'll be at 0, and then I would be at a specific velocity with respect to time. It's going to be flat. It's going to be flat. So in this case, I'm going to be able to get my position versus time graph. If it looks like that, it's going to be a constant. But if I am accelerating, I'm not going to get something. I'm going to get something that looks like a curve. And then over here, if I have a constant acceleration, I'm going to get a line that looks like that. So the whole purpose of that lab was to start making connections between what we actually physically do and what we see it represented graphically. Now, so velocity now is my change in position with respect to time. And a lot of times we can look at that as, you know, if my initial time is equal to 0, so I can do this like this and just do over time if I start with an initial time of 0. Velocity times time is going to just give me my change in position or a displacement. This is always assuming no acceleration. Okay? When I play with these equations, that assumes that I have no acceleration, because I'm just using that graphical representation right there to give you. Now, this, because I'm over a variety of things, can be looked at is called an average velocity. I can also have something that's called an instantaneous velocity, and that's looking at if I'm going smaller and smaller and smaller and smaller on my graph, I can do what we call a limit as time approaches 0. I can do a limit as time approaches 0 of that change in position with respect to time, and this is an instantaneous velocity. And that's essentially what you're reading on your speedometer, is an instantaneous velocity. So we got velocity. I'm going to take it one step further, because you guys have already seen it. A change in velocity, which is going to be velocity final minus velocity initial, change over divided by change in time, time final minus time initial, is defined as acceleration. And we, in general physics, are going to deal only in situations that are using a constant acceleration. Acceleration does not have to be constant, but for general physics, we're going to stick in a constant acceleration world. We're not going to do a changing acceleration. But I have a constant acceleration. Acceleration is also a vector. So let's take a situation. I'm going to introduce it now. I don't think your book introduces it now, but I'm going to go ahead and introduce it now so you can see it and we can start thinking about it as we go along. I'm in my lovely car. And I enter into a curve in my little car. Oh, we'll do it this way. So there's my car. It's going around the curve here. And we're going to enter into the curve. It's going to travel with the magnitude, and usually how we deal with it, when I do this, that means magnitude. It's going to travel with a constant magnitude of the velocity. Okay, it's going to travel in here with a constant magnitude of the velocity. So I'm going to come in here at 27 meters per second, which we know is about 60 miles an hour. And when I come in and I first hit this curve, that's my velocity vector. As I go around the curve, there's my velocity vector. As I go around the curve here, there's my velocity vector. And I come over here, and there's my velocity vector. The magnitude of this vector is the same, but its direction is not. The magnitude is the same, but the direction is not. And if I look at this, I actually end up with a change. And the change is related to the related to the direction. So because I have a change in direction, I do get an acceleration. And we find that that acceleration that I end up with is always going to be center seeking. It's always going to head center of our curve. And that's where we get centripetal acceleration. We usually refer to it with a C. And if I look at this, you can actually get in there and get that this is v squared over r, which is the magnitude of the velocity squared divided by the radius. Now if I look at acceleration, let's look at the units. This is meters per second, and this is seconds. This gives me my units for acceleration are meters per second squared. Those are the units. Now if I go over here and look at this, this gives me meters per second squared divided by meters. That gives me meters squared, seconds squared, 1 over meters. One of these goes away, and I end up with the same units, meters per second squared. So your units are actually going to help you out to make sure that we're dealing with different things. So we will see this. I'm not sure it shows up in chapter 2 just yet, but I want you to see that it's this changing direction that also produces an acceleration. Change in direction also produces acceleration. So, we can play with it and get there. Because this way you can start working homework and we can start looking at other things. You're gonna end up with is if I'm at no acceleration, distance or displacement is going to equal velocity times time. And right now we're in one dimension, so I am not going to worry about putting my vector signs on here. Because we're only going to travel back and forth, up and down. So if I have no acceleration, my distance is going to equal velocity times time. When I have acceleration, and we're in this special case where the acceleration is constant, my final velocity is going to equal my initial velocity plus my acceleration times time. And we can get that equation from my change in velocity with respect to time is equal to acceleration. So I get my change in velocity is equal to acceleration times time. And all I did was clean it up and extend this out. So this is one equation. The interesting thing about this equation is it's got velocity, acceleration, and time as my variables. We're going to get another equation, and it's going to be my change in position is equal to my initial velocity times time plus 1/2 the acceleration times time squared. And I will do that on Wednesday when we come back, show you how we get there. But using these two equations, and so the variables for this one are position, acceleration, and time, because that initial velocity is usually known. I'm either at 0 or I'm at some known velocity. But these right here are my variables. And then the third one, because I have those two equations, I can use these to rearrange, and I can get that V final squared is equal to V initial squared plus 2A change in position. I get rid of time. I don't have to know time to use this one. And so my variables are velocity, acceleration, and position. So all this one does is if I have these two equations, I can solve for time, plug it into this one, and I can come up with this equation. And I want to get rid of time as a variable. I'll show you how we get this one on Wednesday. But these are my three equations that I have. So essentially what you have is I got a screwdriver, a wrench, and a saw. I got a toolkit. And depending on how my problem is worded, will tell me whether or not I need to use my screwdriver or my saw, or whether or not I have to use my wrench. There's one example, and it's the example, and this one I strongly encourage you guys to go look at that'll help you get started with Chapter 2 homework, is we have a person at the top. Actually, let's go ahead and work through that. So let's talk about one-dimensional motion in the y direction. Okay? If I'm walking across here, I have no acceleration acting on me, unless I am in a car and I'm pushing the accelerator pedal. Okay? In the y direction, that's not correct. I have a ball, and it's going to fall, and there's an acceleration due to gravity. And that acceleration due to gravity is going to be 9.8 meters per second squared. That's usually what we're going to use. If I need it for 3 significant figures, it's going to be 9.81 meters per second squared. When we measure it in class, because that's what the lab is next week, it's going to be 9.79 meters per second squared because of where we live. But it's a constant, and we're going to use this primarily as our constant. If I happen to be in the English units, it's 32 feet per second squared. So even if the problem doesn't give you the acceleration due to gravity, and we're in the y direction, and we're dropping a ball, or we're tossing a ball into the air, the acceleration due to gravity is implicit in the problem. So it's a piece of information that you know, even if they don't clearly state it. It's a piece of information that you know. So if I have a ball and I toss it up in the air, the idea is the ball is going to come straight back down. That's motion in one dimension. Okay, that's motion in one dimension. Now, for right now, I'm going to draw this out just a little bit so that we actually can see what's happening. Okay, so I'm actually going to spread it out. We can still make the assumption that it's in one dimension. If I'm tossing the ball, I might have an initial velocity, and my initial velocity is going up. Because of the physics of the motion and what's happening, you know the velocity at the top. What is the velocity at the top? It's 0. Because at the very top, I'm changing from an upward velocity to a downward velocity, and at that change in direction, I've got a 0. The velocity is instantaneously 0 at the top. So when we look at these problems, I've got an instantaneous 0 at the top because of this change in direction. Because I'm going up here, and then I start falling back down. So we actually have another piece of information that we can utilize. So if I'm tossing the ball up, I know the velocity at the top. We also, if we're in the y direction, we also know that we have an acceleration due to gravity that we usually use as little g, and I can draw it in my picture. So let's say I toss the ball up at 3 meters per second. I can use my toolkit now to find out how high the ball goes up. Maybe. Because I know the final velocity at the top, I know my initial velocity, I can find the time that it takes to get to the top. So I can find the time that it takes to get to the top, because I know what the acceleration is. So we can do that one. Let's find the time that it takes to get to the top. V final is equal to V initial plus my acceleration due to gravity times time. I have to account for my direction, so I'm going to put in a minus, because my initial velocity is going up, and we say that's positive. Gravity is going down, we say that's negative. So I have to put that in. At the top, the velocity is 0, so my final velocity is 0. I have 3 meters per second minus 9.8 times time. The only variable I don't know is time, and that's what I want to solve for. So I'm going to get 3 meters per second is equal to 9.8 meters per second squared times time. I'm going to get 3 divided by 9.8, and this is going to be meters per second, seconds. Those meters per seconds cancel out. That seconds comes on top, so my answer's in seconds. So I've used my units to help me out. This gives me 0.31 seconds. So if I toss a ball up with a 3 meter per second velocity, it's going to rise up, and at 0.31 seconds, it's going to start falling back down. And we could start looking at, so there's an example in your book. Another blank piece of paper. Yay, got another blank piece of paper. Here we go. Another blank piece of paper. So in your book, you have somebody at the top of the building. They're going to toss the ball such that it just misses and it falls down. You end up using this as your 0 point, and you can break this piece up into different sections. And this example in your book is really, really good to look at in order to figure out some of the homework problems. That's where I'm going to stop. You've got enough to get you started on the next set of homework. We'll do more on Wednesday.